This presentation is on the scientific method. The goal of employing a scientific method is problem solving, or to find explanations for observed phenomena in the natural world. There isn't a defined recipe, like you might believe, but instead the scientific method uses common sense and logic. So there are many different scientific methods, because there are many approaches to solving problems. At the very root of the scientific method lies causation. We approach a problem and design experiments with cause and effect in mind. We are looking for cause and effect in science. Posing a scientific question begins with accurate observations. Observations should be objective. That means they're not subject to opinion or to bias. They also should be empirical. That means they are measurable. Let's have an example. You like to hike, and you like to hike in Pennsylvania's Cook Forest. So on several hikes, you listen to a group of crickets as you rest on a rock in a clearing. You're surprised because each time you're there, you hear the crickets chirping at different rates. On March 21st, at 6 o'clock in the morning, the crickets are chirping at a slow rate. You go back for a hike in June, and at 2 p.m. you hear the crickets chirping at a fast rate. And finally, in September, you go back at night. At 8 o'clock in the evening, the crickets are chirping at a medium rate. So what are your observations? Clearly, the crickets are chirping at different rates. Yes, but why are they chirping at different rates? What might be influencing the difference? The observations were made during 3 seasons and 3 different times of the day. Of course, crickets can't tell time, and they don't recognize seasons, so it has to be something that's going on during that time of the day or that particular season. For example, the first observation was spring in the morning. It was probably cold, and there probably wasn't much sunlight at 6 o'clock. The second observation was made midday in the summer. It was probably hot and possibly sunny. The third observation was made during a fall evening. Not as hot as summer, but not as cold as spring. And probably the light was low and it was getting dark. So there are some different aspects to these times that might explain why these crickets are chirping at different rates. From our observations, the first thing we do is pose a research question. The observations might be made by you directly. Sometimes it's going to be by reading the scientific literature. The ultimate goal, no matter what, is to determine cause and effect. So the question is going to reflect this. The format of a research question is, what is the effect of something on something? So it is looking for cause and effect. From our observations of the crickets, we can develop 2 research questions. What is the effect of air temperature on cricket chirp rate? And what is the effect of light level on cricket chirp rate? From our research questions, then, we develop hypotheses. It's important to remember that hypotheses are not guesses, but instead they're predictions of the outcome based on observations. We can't just pull a hypothesis out of thin air. We have to have a reason for putting forth a hypothesis. From your observations, you could derive a hypothesis based on temperature or on the amount of light. These 2 hypotheses would be called competing hypotheses. Both could be tested, but both would have to be tested individually. A hypothesis is typically written as an if-then statement. If the air temperature is hot, then the crickets will chirp at a fast rate. Or, if the light level is low, then the crickets will chirp at a slow rate. Ideally, we want to define hot, low light, fast rate, slow rate, for example, because these terms are subjective. Sometimes we write a null hypothesis for our experiments. A null hypothesis assumes that the independent variable will have no effect on the outcome, the dependent variable. Now, it doesn't seem to make sense that you would write a hypothesis like this, because certainly if you're doing an experiment, you expect things to be different. But this is done from a statistical vantage point. The goal of statistical hypothesis testing is to estimate the probability of getting your observed results under the null hypothesis. By statistically comparing the differences in the results of the null and alternative hypotheses, a clearer interpretation of the results can be made. So essentially, we're looking to show that the alternative hypothesis is giving us results that the null hypothesis is not. In a scientific experiment, there are 4 types of variables. The first is the independent variable. This is what is manipulated or changed in the experiment. There can be more than one independent variable, but each must be tested separately. The dependent variable is the results. The results are dependent upon the independent variable. Controlled variables are also known as constants. This is often confusing to students because they confuse controlled variables with controls. Controls are not the same as constants. Constants are the aspects of the experiment that are held the same for each group. Finally, there are confounding variables. The word confound means to confuse. So confounding variables are sources of error. These are variables over which you have no control, but you know may be influencing your results nevertheless. So putting this all together, we write a research question: what is the effect of the independent variable on the dependent variable? Or for our experiment, what is the effect of air temperature on cricket chirp rate? From then we derive a hypothesis: if the dependent variable, then the dependent variable, written as if the air temperature is over 80 degrees Fahrenheit, then crickets will chirp faster. Our null hypothesis for this experiment would be if the air temperature is over 80 degrees Fahrenheit, then the crickets will chirp no faster than at any other temperatures. Experimental controls may be used for comparison. Controls are not subjected to the manipulation, but they are often treated with a placebo. This is common in clinical trials, for example, when one group is given a pill and the other group, the control group, has to have something to take as well. We call it a placebo or a sugar pill. Positive controls show the reaction that is expected, whereas negative controls show no results. It's a real problem if your negative control shows some type of a result, and if that happens, then you have to discard your experiment. Now, it's really important to remember that not all experiments have controls. Sometimes students get crazy trying to figure out what is the positive control or a negative control for an experiment when there really isn't one. Remember not to confuse controls with constants. Controls are for comparison. So let's design a controlled experiment to test the hypothesis about cricket chirp rates and temperature. The hypothesis states if the temperature is above 80 degrees Fahrenheit, then crickets will chirp at a fast rate. 2 groups of crickets will be chosen. So we'll go to the pet store, we'll randomly select, say, 50 crickets, and we're going to isolate them in 2 different aquaria. One group is going to be kept at a constant 81 degrees, that's our independent variable. The other group is going to be kept at a constant 75 degrees, which is around room temperature. That would be our control group. The bedding, the food, the water, the lighting, any kind of stimulation like noise in the room will be the same for each aquarium. So these are our constants or controlled variables. From that, then we will measure the chirp rate in 1 minute. We'll do this every 10 minutes for 30 minutes. So our chirp rate per minute is considered the dependent variable. Once we've gathered our data, we put them in a table. So this is a hypothetical table showing us the condition of 81 degrees versus the condition of 75 degrees. And you can see that the chirp rates are pretty similar at 81 degrees Fahrenheit. And they're also similar at 35 degrees or 75 degrees Fahrenheit. And they appear to be higher at 81. Chirp rate appears to be higher at 81 than it does at 75. So the next thing we want to do is analyze the data. The chirp rate is consistently higher at the higher temperature. However, we don't know if this is a significant difference. In order to determine that, we would have to do statistical testing. From this, then, we would determine if the hypothesis is supported or rejected. Important to remember that hypotheses can never be proved. We support them or reject them. We also want to identify confounding variables in our experiment. For example, we did nothing to separate males from females. Is this going to have any type of effect on their chirp rate? And the conditions in the lab are not the same as those in nature, so this adds a confounding variable to our data analysis. Okay. We also, after analyzing the data, want to suggest additional experiments to test the hypothesis. So we go back and revisit our hypothesis. The data then are graphed. Graphs, also known as figures, provide a visual explanation of the results. Typically, the dependent variable is graphed on the y-axis and the independent variable is graphed on the x-axis. You can remember the mnemonic to help you to remember, you can remember the mnemonic dry mix to help you remember how to plot the data. The dependent or responding variable goes on the y-axis. That's for dry. For mix, the independent variable, which is the manipulated variable, goes on the x-axis. So manipulated, independent, x-axis. Dry mix will help you to remember what goes on which axis. Axes are always labeled, and units are included if it's appropriate. A key must be present if it's not immediately clear what the lines or bars represent. And we have a title on our graphs. The title is going to be the research question turned into a statement, the effect of something on something. Now the question arises is what type of graph do we use? Line graphs and bar graphs are commonly used to represent data. In general, you want to use a line graph if there appears to be a linear relationship, either direct or indirect, between the dependent and independent variables. Remember, a line graph tells the observer that the interpolated values, those values between the data points, are expected. So when we see this graph of Sarah's car, shown on the y-axis showing the value of her car in 2001 versus 2007, if we were to test this actually right in between in June of 2003, we would expect Sarah's car to be worth exactly this amount. By connecting these dots, we assume the relationship is linear. A bar graph is appropriate if a clear relationship is not inferred between the two variables, if the independent variables are not related to one another, or in other words, they are discrete, or if the researcher does not assume that interpolated values are expected. Here we see a bar graph. The bar graph is showing us the number of ice cream scoops sold in the months of the year. So May, June, July, these are discrete entities. So we wouldn't want to connect the dots here because we are looking at the number of scoops in a given month. Okay, so think about the data that we just analyzed, we just gathered on the crickets. What type of graph would you choose? Did you answer a bar graph? If so, you're right. What values are plotted on the x-axis? Time in minutes would be plotted on the x-axis. What values would be plotted on the y-axis? The y-axis would be your results, the average chirp rate in minutes. What would be an appropriate title for your graph? The effect of air temperature on cricket chirp rate would be appropriate. And finally, would you need a key? Most likely you would. There are two sets of bars on the graph, each representing a different temperature, so each must be identified. So now, using a graphing program, you can make your graph, and this is what it would look like. You can see that the dark blue bar is representing 81 degrees. The cooler temperature at 75 degrees is represented by the light blue bar. You can see that in each case that the cricket chirp rate is higher at 81 degrees. We don't know if this increase is significant, However, more testing and collecting data at more temperatures could prove to show us what the result is.